Welcome to the gamma function again and again. We're meeting for the third time to discuss the significance of this most important non-elementary function in all of the mathematics, the natural sciences, and of course the probability and statistics. The title of the lecture is the Weierstrass gamma function, which comes obviously from Euler the Great. I spelled out gamma while using the third letter of the Greek alphabet, the capital letter gamma. As you remember, we discussed the three formulas of the gamma function: the improper integral formula, kind of the continuous structure, very important. In the complex analysis, the probability and statistics, because it really helps us to calculate different statistical moments of the important exponential probability distribution. The second formula, the Euler-Gauss formula, I exactly derived it in two ways, from the Euler's perspective and from the Gauss's perspective. What's important about this formula? It has a computational approach of the gamma function, because sometimes the improper integral is not easy to calculate. Computational is just way easier. Just the product, the factorial, power, take the limit, and you have your gamma function. The third formula we discussed, that's the Euler's infinite product of the gamma function. It has connection with the infinite series, with the number theory. It gives us information about the poles and the zeros of the gamma function. And the fourth, today, I'll follow this red arrow. That's the formula in the red box, that the Weierstrass formula of the gamma function. It also it's represented as the infinite product, which has those two important constants of the mathematics, the Euler's constant and the Euler's number involved in this case. This formula also has connection with the infinite series, number theory. It gives us information about the poles and zeros of the function, and it's very useful in the complex analysis. So what about the poles? Obviously, dividing by x0 is a problem. It blows up. 0 is a pole, and our index k runs from 1 to infinity, or positive counting natural numbers. So each time our x input argument is equal to the negative integer number, when it's divided by the corresponding positive integer, we have -1 here. 1 plus -1 is 0. So with 0 in the denominator, we're dividing by 0. It's a problem. Blows up, all those positive values being divided by 0. Blows up, positive, negative numbers there. So we have poles for the non-negative integer numbers, and we discussed function is defined for the positive input argument, which means that all the terms will be positive, positive, in positive. So will be the product of the positive terms, which means that for this domain, the gamma function will have no roots, no zeros, always positive. And also, if we evaluate the logarithm of this infinite product, look at differentiate it and look at the derivative of the gamma function at the point of 1, it will be equal to minus constant gamma, the Euler's constant. We will also use this fact proved by Euler, that the limit of the harmonic series minus the log n, he assumed log n base e, natural log, actual ln n, he proved that it's equal to a constant using monotonicity, was bounded below monotonic, the constant approaches to this constant. Euler himself called that constant C or O. He never called it gamma. Just later in the 19th century, they decided to call it gamma because it's being used in the gamma function, both discovered by Euler. So they decided to assign it a gamma lowercase. So this limit actually means, if you want to write without the limit, it means that the harmonic series is equal to log n plus the gamma Euler's constant. plus the infinitely small value depending on the n index, which means that the limit of alpha of n goes to infinity is equal to 0. Euler exactly proved that. We discussed it. You all know, you all remember that. Now let's look what Weierstrass did. He took the Euler-Gauss formula, he modified it. So I can rewrite this limit. M power of x is actually equal to ex log m. And again, math is like playing chess. When you make a move, you need to predict the outcome of your move. You need to see what will happen as the result of it. So what if I bring the feature of this harmonic series under this power? So what if I subtract the harmonic series from here? Minus up to 1 over n divided by this x, first x. I'm going to split it into second fraction. So I need to compensate those extra values by multiplying my ex here, harmonic series, 1 plus 1/2 plus so on, plus 1 over n, yeah? And divided by, so x plus 1 by x plus 2 up to x plus n. That's not it. I still have my factorial. I'll bring it down there. So we over 1 over 2 up to over n. So I have this kind of partial product here. Now, this difference, using the Euler's discovery, the harmonic minus log n limit and infinity is equal to gamma. Here we have this difference is flipped, so it will be just equal to minus gamma, yeah? So this is e minus gamma x over x up front of the limit, because limit depends on n, kind of a constant. So it's equal to, actually, e minus gamma x over x. Here we have a limit of this partial product, n goes to infinity. What I have here, I can rewrite it ex multiplied by ex over 2 by ex over 3, and so on. The last term will be ex over n divided by, so I have 1 plus x here. The second term will be 1 plus x over 2, and so on. And the last term will be 1 plus x over n. You can see it's a partial product here. So it's equal to e minus gamma x over x, the limit, m goes to infinity of this partial product. Now I can write, my general term will be here. Look at this. My denominator changes 1, 2, 3 up to n, so it's my index. The same thing here. So it's equal to e x, let's say, over k divided by 1 plus x over k. K runs from 1 to n. Yep, almost there. And when n goes to infinity, k will run from 1 to infinity, and we will arrive practically to the Weierstrass formula. So exactly equal to, it's equal to e minus gamma x over x. In the infinite product, now k runs from 1 to infinity. I hope that's clear. And my general term is, I can just rewrite my denominator up top, negative power 1 plus x over k power minus 1 e power x over k. And this is equal to actually a gamma of x. This is what Weierstrass gamma function. This is the Weierstrass gamma function. exactly, we just arrived to that formula. The gamma function, the Weierstrass version of it. I hope that's clear. Also, I called Euler the other day. I told him that Weierstrass used his and Gauss's Euler-Gauss formula. He came out to this version. I asked him, your highest knowledgeness, could you please derive this formula using your results more authentic? He told me, yes, I can tell you another way of deriving it. And this is what he told me. He told me, try to evaluate my number raised to the power of my constant, Euler's number to the power of Euler's constant, while using my discovery, the existence of the Euler's constant. Let's look at that. So this is what he showed me. He actually evaluated e to the power of the harmonic series 1 plus 1/2 plus so on plus 1 over n, and it's actually equal to, that's the Euler's great result, e to the right hand side will be e to the power log n, e to the power gamma, e to the power a of n. Again, Euler used log, assuming that the base was e, ln actually. He didn't use ln notation. The base was e. This is how, this is what he used. And actually it's equal to e log n. That's basic log property. You all know that. It's n, e power gamma, e power alpha of n. Now, next step, he told me, like, what if we divide it by n plus 1 again? You need to predict the outcome of this step. So this is what we have. What if I take my e to the harmonic power, harmonic series, and divide it by n plus 1? So it will be actually equal to this thing, n divided by n plus 1, e gamma, e alpha, n. Yeah? The left-hand side actually represents the partial product. Let me rewrite this partial product. It's equal to e to the power of 1 multiplied by e power 1/2, e power 1/3, and so on, e power 1 over n, and I divide it by n plus 1, and it's equal to n over n plus 1, e gamma, e alpha of n. So the last term is divided by this denominator. All of those e terms, we're trying to create a partial product. So I need to have denominators here. This is what we'll do. I will divide it by n and multiply it by n. Divide by n minus 1, multiply by n minus 1. N minus 2, and so on. So this way, all the fractions will reduce each other. N reduce. N minus 1 reduce. And so diagonal reduction of all the fractions, and I will end up at n terms from n to 1. So if I move from n plus 1 down n terms, I will finish at 2 exactly. Yeah? The last term will be 2, which is the next will be 3 over 2 actually. 4 over 3, and so on. Yeah? So this way, I will have all of those diagonal reductions, 2, 2, 3, 3, 4, so on, and we'll just end up just n minus 1. So nothing's changed. The value is preserved. I just rewrote it as the partial product. So you can just call it partial product, I can write it general term here. You can see it's e to the power. My denominator changes from 1 to n. So 1 over k. K runs from 1 to n over, and the general term in my denominator will be just 1 plus 1 over k. You can see my denominator changes from 2 over 1, 1, 2, 3, up to n. So I can rewrite it as 1 plus 1 over k. K runs from 1 to n. You can see when k is 1, so it will be 1 plus 1, 2. When k is 2, it will be 1 plus 1 half 3 over 2. When k is 3, will be 1 plus 1 over 3 is 4 over 3, and so on. So everything in Greece here, yeah? So this is what we have a partial product. So you can call it, say, Pn partial product. So this partial product is equal to that product, yeah? Now, if I take a limit of this partial product when n goes to infinity, I'll get an infinite product, yeah? Which means that the limit Pn n goes to infinity, it's actually equal to the infinite product. Now k runs from 1 to infinity of the same general term 1 over k over 1 plus 1 over k, and it's equal to the limit of that, yeah? It's equal to the limit of n e gamma e alpha n over n plus 1. N goes to infinity, and that's an easy limit. You all know that this value goes to 1. Yeah? E to the power also goes to 1, yes, because using the Euler's result, alpha n goes 0, e0 is 1, and over that is 1, so it's finally equal to e power gamma is equal to this infinite product. So this is what we did. We just evaluated Euler's number into Euler's raised to the Euler's constant as the infinite product. Now let's look at e power gamma x. Very easy. So finally, so e power gamma of x, gamma x, it's actually equal to e gamma and power x. So e gamma is equal to this infinite product raised to the power of x, which means that every term will be e raised to the power of x. Simply just infinite product, k runs from 1 to infinity. Here I have e power x over k over 1 plus 1 over k power of x. So this is a wonderful result. We will call it the 2-star formula. That's this. We just evaluated e to those powers as the infinite product. And now, let me just multiply those two infinite products, and there will be nice cancellations and simplifications there, and we will arrive at the Weierstrass version of it. Yeah? Let me continue here. Now, let's multiply the 1-star multiplied by the 2-star formula. And finally, what I will get. So we'll multiply 2-star by the 1-star. That is my gamma of x plus 1, which is equal to gamma of x multiplied by x, yeah, and I multiply by the 2 stuff, by E gamma x. And it's equal to, so I need now to multiply those two infinite products. So it will be capital pi, will be nice simplifications there. Okay, 1 to infinity, 1 plus 1 over k power of x over 1 plus x over k, multiplied by another infinite product, k runs from 1 to infinity, e power x over k over 1 plus 1 over k power of x. As you can see, there's nice reduction of the fraction there. And finally, I have the same infinite products, the same indices. I can combine them under one infinite product, which is equal to this infinite product k from 1 to infinity, just exk over that, yeah? So ex over k over 1 plus x over k. We're almost there, yeah? Practically finished. So it's equal to gamma x e gamma x. So from here, my gamma function will be equal to exactly, finally, from here, gamma of x is equal to, gamma of x will be equal to, so if I move e here, will be minus power divided over x, so it will be e minus gamma of x, e minus gamma x divided by x, and multiplied by this infinite product. K runs from 1 to infinity, e x over k over 1 plus x over k. That's the wonderful result. That is the Weierstrass formula of the gamma function. It was derived in more authentic Euler way. As you can see, just write to the Weierstrass version of the gamma function, e minus gamma x, infinite product, e x over k, x over k, divided by that, which is the same thing, 1 plus x over k, power of minus 1. I just showed you two ways of deriving the gamma function. As you can see, you can Google gamma function, you can come up, you can see so many versions of the gamma function. You can also come up with your version of the gamma function. For example, if you take the Cinderella's crystal shoe formula, bring it here, blend it in, and you may be able to come up with your own version of the gamma function. No problem, as long as it's correct. I hope that was clear, interesting, useful, informative. I also hope you enjoyed it. Thank you for your time. I'll see you soon in my future clips. Thank you. Bye-bye.